Okay, picking back up again, let me begin with defining coordinate functions. So, I mean, they're kind of the obvious things. So xi is a function from Rn to R, defined in sort of the obvious way. X sub I of p is just equal to p upper I, okay? And that's obviously for I1, 2, all the way out to n. Of course, in R3, for R3, we also allow ourselves the simpler notation, right? Like x of p is just p1, y of p is p2, z of p is p3. Okay, great. So these are the coordinate functions. Coordinate functions on R3. And so this is a notation which may be a little bit new to you. So for example, I can write functions with this notation in a kind of sneaky way. Like for example, this is not sloppy notation. I can actually write f is equal to, say, x. Well, I guess this would be ambiguous until I write this, plus yz, right? What this means then is that actually is this function is equal to the x squared, x times the x function plus the product of the y and z functions, you know, usual multiplication and addition of function rules. Just like, so for example, if I was say f of abc, well, that would mean a squared plus bc, right? That's what this implies, all right? Or another example, you could have f equals to, say, sum I equals 1 to n of x upper I quantity squared, right? This would be the distance squared function. So if I would plug in a point p, well, what I get out is basically the length of that point viewed as a vector squared. All right. Now this brings us, so that's sort of fundamental stuff. But the more interesting thing we of course study in Calculus 3 and elsewhere is the so-called directional derivative, right? So how do we define the directional derivative? Well, here's the main difference, advanced calculus, and here also. We don't assume that we only define directional derivatives for unit vectors, okay? So we're gonna let f be a function. So the domain of f is some subset of, say, Rn. Real valued function, great. We're going to assume that the function's smooth. Probably only need first and maybe second derivative usually. Smooth, and suppose p is an element of the domain of the function. Okay, great. Then the directional derivative of f at p with respect to, let's say, p comma v, the vector v attached to the point p, which would be an element of TPRN as we learned. And here's the notation I'm going to use. So the df, that's the directional derivative of v at p, okay. So sometimes I'll just write this df of, we could write it df of p comma v. I mean, that'd be fine, whatever. Don't make too much of the notation here. Anyway, so limit as t goes to 0 of what? Well, of f of p plus tv minus f of p over t. All right, great. That's pretty much what you did in multivariate calculus, right? You should notice that what we're really doing is just feeding a parameterization. You know, we've got a line, right? Got some line, it has some point of attachment p, and it's got some direction vector v, right? So you can think about v going along that line, and you could say, so alpha alpha of t would be p plus tv. That's a parameterization for the line, right? So what we're really looking at here, if you look at the definition, is the limit as t goes to 0 of what? Well, it's really f of alpha of t, right? Minus f of alpha of 0 over t. At which point you go like, wait a minute, that's nothing more than what? Well, that's exactly the derivative of the composite of f and alpha prime of 0. All right? But hey, that we can use the chain rule and rewrite that. Well, what is that? Well, that's just you know, that's the sum, assuming f is smooth, right? Sum I equals 1 to n of partial f partial xi at alpha. Well, I suppose of 0, fine. Of course, that's just p, right? Times, well, x sub I, upper I rather, of alpha. And I'll plug in 0, okay, fine. Goodness gracious. Oh, I've forgotten my d of all that. Well, I'm plugging in 0 at the end of it, not the start of it, so find t. Alright, now I've made a mess of it. I'm going to go to the next page, but the point is we're going to get the clean it up here. What we have, of course, is nothing more than fine. It's written nice in the notes. This is the. That's exactly going to just what is that? That's, you know, x upper I of alpha of t. Well, that's just p upper I plus t vi. So if you differentiate that with respect to time, it just selects the ith component of the vector, right? It just picks off this piece right here. So this just differentiates to pvi, and of course this here is p. So what we get is sum I equals 1 to n of, and I'll bring this is vi, so I'll bring that up front though to make a point here. So partial f partial xi at p. Now, of course, you may recognize this. This is, right, I mean, what we're really looking at here, you've probably seen it written, you may remember it written in this way. That's really like v dot the gradient of f at p, right? That's the formula we actually use to calculate directional derivatives in the context that v was a unit vector, right? That's what you often actually do in multivariate calculus as far as directional derivatives. I think most students, in fact, it wouldn't be surprising to me if many students left the course knowing this formula as the directional derivative, forgetting, in fact, that that's actually how we defined it, right? But anyway, so that's a, I should probably just write that down again real quick here. 5. So the point then is that we can express, well, for nice enough functions at least. I'm going to skip the fine print here and just get straight to the formula which matters, which is that the directional derivative of f at the point, well, you know, applied to the vector v attached to the point p. Well, what is it? It's just the sum I equals 1 to n of the vi partial f partial xi at p. All right. Yeah, horrible handwriting. Now, that's lovely. And it brings us actually to, here's the thought. So, if we write this a little bit different, you can express this also as being the sum I equals 1 to n. My paper's bouncy. Let's see, vi partial xi p. So this is just another notation, all right, like that. And so if you really think about it, this expression right here in the parentheses, it's really interchangeable, right, with p comma v. I mean, and that's what we do. We make a new definition. We replace the tangent space. Oh, that Previous definition for tangent space only lasted about 20 minutes, oh well. You can forgive me. But here's going to be what we're going to work with by default going forward. So the tangent space P of Rn, we're going to define it actually, okay, to be something like this. Sum, and I'm going to use j for change. J equals 1 to n of Vj partial x j applied to the point P, such that, well, v1 vn, well, that's just an element of Rn, okay? So these derivations, all right, these differential operators, contain all the same information as P comma V as far as we're cared. I mean, they tell us that it's attached to the point P, right? And they've got these components, these v1 through vn, so they've got everything we need to capture the idea of a vector. And in this notation, all of a sudden, we get the directional derivative. Well, what is the directional derivative then? Well, if I oops, wrong. I'll eventually find the one I want. I have this, right? df of the vector attached to the point P, the directional derivative of that, it's nothing more than Vp acting on f. See, if you think of this as being V attached to P, this operator then is what we're calling the vector attached to the point P now. So such a Vp, you know, v1 partial x1 at P and so forth, is an example of what's called a derivation. It's a derivation on the set of smooth functions, okay, that go through the point P. And so it's worth taking a second here to catalog the properties. What are the properties here? Well, properties, this is my proposition 1.2.7, all right. So again, for nice enough functions and x, so we have x of, first of all, if we have x of fg is equal to well, x of f times g of p plus f of p times x of g. Now here x is a element of the tangent space to P at Rn, which again I'm just telling you now is a set of derivations at the point P. It's something of this form, right? This is the quote-unquote x in my next proposition, all right? Anyway, you also have linearity. I mean, I'm writing additivity at the moment. So x of sum is sum of x acting on them, all right? X of, so you can pull a constant out. And perhaps more excitingly, oh, no, nothing exciting here. I'm thinking of another one. So those are the properties of derivations. And if you want, I mean, what's the proof? Well, the proof basically just apply the properties of, you know, partial derivatives. To the definition of our newfound definition of tangent space, right? So this gives us a way to look at, and in fact, I guess the thing I should mention is I define the tangent space in terms of derivations, in terms of a coordinate system, the Cartesian coordinate system. Of course, we've gotten used to using the Cartesian coordinate system, right? But there'll soon come the time where you want to be able to write things without a specific reference to coordinate systems, and so this would be a bad definition in that viewpoint. On the other hand, if you were to use the properties down here, that it's that it obeys the product rule, or the Leibniz rule if you like, and that it's linear, well, these two things put together give you the algebraic characterization of what's a derivation. And you could use these three identities to define a derivation, and then you could say TPRN is the set of all derivations on the set of smooth functions, all right? But you notice that I just claimed that I didn't define it. My definition is much more clumsy, let's say, but the one we're going to use because we're starting, all right? Now, of course, we can also talk about vector fields, right? A vector at a point, well, a vector field would be something like what? Something like this, x equals to f1 partial x1 plus f2 partial x2 plus plus fn partial xn. And so I'm suggesting if you drop, there's sort of the obvious thing. What would x at the point P be then? Well, these f1s through fn's are functions, right? And so x of p, well, you just plug in the point of the component functions, right? And you take your partial x1 and you put p on it, and so forth, right? So we can talk about vector fields. The difference between a vector field and a vector, of course, would be a vector at a point has components. The components of it, the v1 through vn, they're just numbers, right? The components of a vector field, the f1 through fn, they'd actually be functions, all right? And the vector field, the set of vector fields, doesn't have a vector space structure because the coefficients being functions are from a ring, not a field. There's some sort of what's called module structure there, anyway. Okay, so trying to move along eventually. Sorry, I'm moving so slow. So if we go back to our, now we have this lovely definition of tangent vector, right? And so we can, as an application of this, we can calculate what's the directional derivative. What's the directional derivative on the ith coordinate function, right? In the, let's say, direction of the jth coordinate function at p. Well, all right, so by definition, this is partial xj at p. Well, I mean, it's not by definition, it's by the proposition 1.25 we just worked out. So we say we take the vector, right, viewed as a derivation, and you feed it the f. In this case, f is x upper I, so I feed it xi, right? So that's partial xi, partial xj at the point P. Hey, what's that? Well, that's the Kronecker delta, ij, right? And so what we find out is that this thing, well, so if you look at this, what is dxi? Well, dxi is a function. If you strip away, think about dxi just on its own, it's really what? It's really a function from TPRN, right, to R. I mean, that means that dxi is an element of the dual space, right? The dual space to the tangent space of Rn. So the dual space, remember, to a vector space is what? Well, if V is a vector space, V dual is the linear transformations from V to the underlying field for SR. So the so-called linear functionals. This is finite dimensional, nothing too fancy schmancy. Anyway, so dxi is a dual vector, or you could say a covector, and in fact, it looks like it has just met the condition for the dual basis to these guys. So, in fact, if you really take a look back at things, you see that the standard basis is being represented by partial x1 and so forth here. Partial x2 would be like E2. And on the flip side, this dxi is, well, it's the dual basis, like we would write E upper I in linear for it. Okay, so that brings, we make a definition then. It's too important to keep referring to it by the directional derivative, so we make a definition. We say that dp x upper I acting on a vector v attached to p is equal to vp of xi. Actually, that's a special case of a more general definition. This is for each vp in the tangent space to p of Rn and I in n sub n. Okay, so I mean actually this definition, we make the general definition shortly. Let me just get it over with. dpf acting on vp is just defined to be vp acting on f. This is the so-called differential of f. F at p. All right. You can see, right, dpf is an element of the dual space to the tangent space at Rn, because it takes in a vector and it spits back a number. All right. But the larger point here is that let's just collect our thoughts. That we have something really, really nice. We have the tangent space to p at Rn has a basis, well, partial x1 p all the way out, partial xn p, whereas the cotangent space, so-called TPRN star, has basis, well, dpx1, dpxn, and this is the dual basis in the usual linear algebraic sense. All right, so you have this intertwining relation, dpxi, and sometimes we like to use this notation. Partial j at p is just Kronecker delta ij, so they're dual. And of course, you know, we can also talk about the cotangent space and cotangent bundle. I think I'm already talking about them, but let me just be clear. The cotangent space, of course, TPRN dual. It's just well, it's really functions, linear functions from what? From TPRN to R, right? And the cotangent bundle, which you could call TRN dual, or I think sometimes you'll see this T dual Rn. I mean, okay, whatever notation. It's just going to be the union over all the points of P Cartesian product with well, TPRN dual. All right. So it's just attachment of the cotangent space to each point. All right. And you can also talk about an assignment of a dual vector or a covector to each point. And you might be tempted to say that a section of the cotangent bundle would be something, it would represent a covector field, but that's not the language which is used. We don't typically talk about covector or dual vector fields. Those would be, to me, those would be the natural terms. Instead, what we say is, we talk about one forms. So a one form is actually, I mean, to me, a one form field would be the more natural term, but we don't say that. We say one form, or sometimes a differential one form. A differential one form. Differential one form is then something like this. It's alpha, so something like alpha lower 1 dx1 plus dot 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 alpha lower n dxn. This would be a differential one form. And I just, you know, where's the point, right? The point is here, although, I mean, it's not really a very interesting point I'm making. Sorry, forgive me. Let's see here, so alpha n p of course, that's the assignment of this one form. This gives us this one form alpha at the point P gives me this specific dual vector in TPRN. Dual, of course. Okay, great. So it's a one form, and we'll study those more in the next lecture. But basically, vector fields and one forms both have functions as their coefficients, and if there's a natural way to put vectors and vector fields and one forms together, like if I if I was to take alpha at one form, and if I was to take x a vector field, then alpha of x would naturally be a function. In fact, you can work it out. This is a nice exercise to work out. This actually ends up just being alpha 1. I guess I was using f1 earlier, f1 plus alpha 2, f2 plus plus alpha n, fn. That's a pretty good, silly, not too silly, but exercise, right? Work this out. And here I'm assuming x had the same form as it did back on page, what was it? You see here. Where did I put that thing down? Where is it? Here, page 5. You see, remember, I wrote x like this with the component functions. All right, and now I'm saying alpha like this with these component functions. I'm saying if you take alpha and you feed it x, then you naturally get this function. Of course, you can put in a point, and then that will give you the things I've defined somewhat carefully today. All right, anyway. So don't get lost in the notation here. We're just, again, it's just mostly a setup. All right. So in summary, let's say, we have defined the differential of a function. And, well, I wrote this before, I'll write it again. So definition, f, domain of f, a subset of Rn. So a real valued function of some subset of Rn, let P be an element of the domain of f, and let y be an element of the tangent space to P at Rn, then dp f, when that differential of f at P acts on y, it does so just by letting y act on f. All right. And the really neat thing is this gives us a actual interpretation to those total differential formulas we wrote back in multivariate calculus. So like, for example, we have df of partial xi, right? Is then, well, it's partial f partial xi, and I can do that at each point. So you can add a point if you like. But oh, there's another exercise I neglected, which was that. By the way, what I also forgot to tell you is that the vector y, I can write it as y acting on the first coordinate function, partial x1 at P, since it's at P, all right? And plug in the point P, okay? So you act on the nth coordinate function and then plug in the point P. So, well, and on the other hand, the one form, kind of similar, alpha, actually, you can write the components of it as, well, at a, stink, I need a point. Curses. At the point P, all right. So that's partial 1 at P, dp, so many points. Let's see here, alpha, partial n at p. So you feed it the nth partial. That gives you the component that comes next to the nth differential. So these are like, how do you find the the components of a vector or a one form at the point? Well, you just feed it. For the vector, you just look at the coordinate, the value of the vector field, the vector acting on the coordinate functions. For the one form, you just let it act on the coordinate vector fields. Those actually give you the components. So the fact that I have this shows me that in fact I can write df, right? Its coefficients, these guys, are just like partial f partial x1 dx 1 plus partial f partial x2 dx2 and so forth and so on. Of course, that's the total differential we wrote in multivariate calculus, but now it actually has an active meaning. It is a one form, a differential one form. If you plug in a point, it's a covector. And more than that, we can capture the directional derivative, and also in terms of this notation. So df of the vector x, which is attached to the point P, is just equal to the differential of P at f, differential of f at P, acting on x, which by the way, of course, is just x of f. Okay, so a lot of this is the reason for this notation. All works together for good, believe it or not. I mean, you can believe what you want. I'm almost done here. And finally, we come to proposition 1.2.12, which is basically on the directional, on the directional derivative of the coordinate. Oh, there's a typo. So this is basically properties of the differential. Okay. So the properties of the differential you may already be familiar with from multivariate calculus, but they're still true in this more sophisticated way of looking at it as covector, or if we let the point vary, a one form. So you have the product rule. You have additivity. d of f plus g is df plus dg. You can pull a constant out. You have homogeneity. d of c times f is equal to c times df, right? And then the one I'll prove, you have the composite. So if I have h composed with f, then that's equal to h prime of f times df. Now here, f and g, they're functions from Rn to R, but this h is a function on R. Okay, so h composed with f is something like you go from Rn to R again. Okay, so this would be f, this would be h. Great. All right. So I'm going to prove 4, and then I'm going to go to Lowe's tomorrow and buy some LED lights because these incandescent lights are killing me. Let's see here. So what we got here? So to calculate d of h composed with f, right? I can use this result that this is going to be the sum, I equals 1 to n, right, of what? Well, of this thing, d of h composed with f, right? And so this is a one form. I can feed it, allegedly, according to this exercise, which you should do. It's not hard, but once you do it, you'll really understand it, what we're doing. So to get the component of xi dxi, I take this one form and I evaluate it at partial xi at p. All right, and then that gives me the coefficient of d p xi. All right, so I really need to calculate this. All right, I need to calculate that. So what is d of h composed with f of partial xi at p? All right, and oh goodness, I guess I have to put a p here, and I probably should put a p here since I've been putting p's in. All right, great. Got out of my system, almost out of my system. There we go. Well, by definition, this is partial. partial xi of p acting on h composed with f. But what is that? That's partial of partial xi of h of f of, well, really, I mean, x1 dot xn, well, don't mean to confuse you here, I haven't used that notation quite. This all being evaluated at the point P, fine, I'm going to put that out here just to get out of the way. Now what I have is the derivative of a composite, right? So I have to do the chain rule. And the chain rule says, in this case, for multivariate calculus, it says that, well, that's h prime, right? Derivative of h evaluated at f of, well, I'm tired of writing, you know, f of x, if you'll forgive me for that notation. And then times what? Well, let's see here. Partial inside function, right? Partial f partial xi. All of this at the point P, right? So when I plug in the point P, I get what? I've got h prime of f of p times partial f partial xi of p. Okay, great. Then what? So then you take that and put it back into the question mark up here, right? And what do we get? We get dp of h composed with f is equal to, well, you see what you got is you've got this derivative term, this piece right here. You think about it coming up in here, it's in every single term in the sum, right? So I can pull it out by properties of finite sums, and then I've got this sum I equals 1 to n partial f partial xi dp xi, right? And this is at the point, the point P. But hey, just like I got done telling you up here, this is nothing more than df at p, right? So what you got is h prime of f of p times dpf. Hey, but that's exactly what we're trying to prove, right? And that's really, really nice because, as I mentioned in the notes, I'm tired of writing. So, I'm going to be lazy for a second here. As I show you in the notes, that's really, really handy because if you want to do something like, say, calculate the differential of f as being, say, f as the distance function here, right? Instead of calculating it directly, I would square it. Then I get the distance squared function. Well, that's easy to take the total differential of because I can just total differentiate this. I get 2x1 dx1 and so forth, right? But let's see if I can zoom in. So, you know, I can make quick work of this problem without ever differentiating a square root by simply taking advantage of this chain rule, right? It's a very important but seldom used technique by Calculus 3 students. Anyway, that's all I got for this lecture 2. Next time, we pick up with, I think, my section, where is it? My section 1.3, which is the wedge product and differential forms. Now, I guess we're a little bit out of order with O'Neill. O'Neill covers curves first, and then he covers this second. But I'm going to go ahead and cover differential forms, then I'll cover curves after that. You know, whichever way you like. By the end of Chapter 1 in O'Neill, we know a lot of things. But we'll know them better as we go on in the book. Anyway, I will shut up. Thank you for bearing with this rather boring lecture.